Alright, so today we're going to take a little bit further with applications of Newton's laws and the four basic forces as well. We'll just hit on those at the very end. So first up, we have an application here where we have two tugboats specifically, that are pushing on a barge. And what we want to do is, you can see the triangle there that's being formed. We can use that with our knowledge of vectors to solve for the applied force to the barge, and then use that to work our way backwards and find the drag force that's acting against the barge. So, because well, in a minute here we'll also know the acceleration. So here we need to take these two numbers that are on here and remember them. So 2.7 times 10 to the fifth is just 270,000. 3.6 times 10 to the fifth is 360,000. So we need to take those with us, because we're going to go down here a little bit on the slides to give ourselves some room to do this problem. So there's the overall picture of the two tugboats pushing the barge. There is the triangle, the free body diagram, as well as the actual vector diagram of it. And so here's the slide that we're going to use to actually do the work on, because it's got plenty of space for us. So I'm going to redraw that triangle. You want to draw the triangle as well. So we have the x direction force, the y direction force, we have the applied force, then the net force, and the drag force. So Fx and Fy we already know, we got from that first slide. That's 270,000 and 360,000. And also on this slide it does tell us the acceleration and the mass that the barge is moving with, which is going to help us with the net force part of it. So let's go ahead and figure out what the applied force is first. Once we do that, we can then focus this as if it were just a one-dimensional force problem. So in order to find the hypotenuse of the triangle using Pythagorean theorem, or the magnitude of the sum of two vectors as well when they're at right angles, it's the same idea. So F applied is just going to be the square root of these two numbers squared and added together. So we get the square root of 360,000 plus, squared. Can't forget that. And there we go, 450,000 newtons. Now, if you notice that we do have what is called a Pythagorean triple here occurring, and that's why it's such a perfect number. That's what happens with Pythagorean triples. They have perfect whole number sides to them. So we have that. Now we need to deal with the net force. So first of all, of course, net force, as always, is mass times acceleration. And in this case, the net force is going to be equal to the applied force we just got minus the drag force, which is what we're looking for. So we have mass, we have acceleration, we have the applied force, we just need to find the drag force. So we're going to set these equal to each other. F applied minus our drag force that we're looking for equal to MA. And again, in the problem here, it gives us our mass is 5 times 10 to the 6th kilograms. That's 5 million kilograms. And that our acceleration, A, is 7.5 times 10 to the negative 2. So it's 0.075 meters per second squared. So plugging everything in, 450,000 minus drag force equal to 5 million kilograms times 0.075. So, forgot which side my calculator was on. There we go. So 5 million times 0.075 is 375,000. So subtracting 450,000 from both sides. Gives us a negative number, but we also have a negative drag force there, so that makes sense. But dividing by -1, multiplying by -1, whichever route you want to go to get rid of that negative sign. Gets us our answer. Drag force is 75,000 newtons. I'm going to jump back to the Nearpod here. So we can see their work as well from the textbook, OpenStax. There they are getting, for some reason they got the angle, but it's already in the pictures, so there's really no reason to calculate that out. And there's the formulas we used as well. F net's equal to MA, F net's equal to the applied force minus drag force, set them equal to each other, and work your way through there and solve it. So there we go. They have it as 7.5 times 10 to the 4th newtons, which is the same thing as 75,000 newtons. So now we're going to get into our tightrope walker that we mentioned at the last video and the last notes. We had one where the tightrope walker was balanced in the middle. The angles were the same on either side, so there's a special formula when that case happens. However, that's not always the case. So here we have this traffic light. It's not in the middle. It is at two different angles. So there's a bit different work that needs to go into this one. Now, one thing is going to remain the same. The tensions going up are still going to be combining together to counteract the weight of the traffic light. So that's going to help us out. I don't remember which slide I used to do this. I think it was this one. Here. Because it has a free body diagram and a picture. So let me take a screenshot of this. Pretty sure I have one actually saved already, but that's alright. And it does tell us on another slide, I forgot to write that down, or mention that the mass is 15 kilograms. So we do have that. So they do have a free body diagram here, but there's more details to it than what they have drawn, because we also have a T1Y, or T1X in this case, a T2X, and going up, we've got two forces, and that's going to be T1Y and T2Y. So now looking in the x direction alone, again, even though they are different angles, T1X and T2X need to balance each other out because it's not moving still, so that needs to be the same. And then the T1Y and T2Ys need to combine together to equal the weight. Remember, again, we use FG for weight. So that's what we're going to set up, right? But we also know that our net force is equal to 0. F net is equal to 0. So in this case, that means looking in the y direction. So FG needs to, well, be subtracted from. So T1Y plus T2Y minus FG equals 0. They balance out. And on the other side, T2X minus T1X equals 0 because they balance out. So manipulating the left side, T1Y plus T2Y is equal to FG, the weight. On the other side, T2x equals T1x. They're the same, which is going to benefit us because we can now come up with some formula there that we can then plug into the other side to help us out. So knowing these things, we also know that T1x is going to be equal to T1. Now x is going along the same angle, so that's the 30-degree angle. So that is cosine of 30. T1y then is going to be T1 times sine of 30. T2x is going to be T2 cosine of 30, 45. Different angles. And T2y is T2 sine of 45. Now, since we're still kind of new to sine, cosine, and tangent, you might not know, but one of these comes out nice and pretty. Helps if your calculator's in the right mode, though. Sine of 30 is 0.5. So we're going to use that to our advantage as well. So this is T1y is really 0.5 T1. And so plugging all of these things into these two equations here, on the right one really is the main one for now, but we're going to do both. So on the left for T1y, we've got 0.5 T1 plus T2 sine of 45 equal to mg. We're going to swap out FG for mg. And then for the x's, we've got, unfortunately, no special things happen with cosine of 30. Cosine of 60, though, is 0.5, but not what we're looking at. So T2 cosine of 45 equal to T1 cosine of 30. Now, we have our option here. We can solve for T1, we can solve for T2, it doesn't matter which one. But we need to solve for one of them to plug it into the other. And so it's kind of up to us whichever one we want to deal with, but solving for T1 might make our lives a little bit easier. So if we divide both sides by cosine of 30, we'll eliminate on the right, we're left with T1 being equal to T2 times cosine of 45 over cosine of 30. And now we can take that and swap it for T1 in the other equation. So that's just going to be 0.5 in front of all of that. But we have this T2 times 0.5 cosine of 45 over cosine of 30 plus T2 sine of 45. And all that is equal to mg. And now we have T2 for both of these. We can just factor that out. So T2 times 0.5 cosine of 45 over cosine of 30 plus sine of 45 equal to mg. And now we can divide that to both sides to get T2 by itself. So T2 is equal to m, we know is 15, g is 9.81, and all of that's going to be divided by 0.5 cosine of 45 divided by cosine of 30 plus sine of 45. And plugging that into the calculator, we can get what T2 is. It's going to be kind of ugly, but it'll work. So that divided by, we're going to throw a fraction in for our 0.5 cosine of 45 over cosine of 30. Again, if you didn't before, make sure your calculator's in the right mode. There we go, 131.93. So that's T2. And now we need to find T1. But on the other side here, we know that T1 is equal to T2 times this cosine of 45 over cosine of 30. So just gotta plug it in. So I'm gonna use this exact answer here. I'm just gonna multiply it by cosine of 45 over cosine of 30. And there it is, 107.72. But you can clearly see that the two tensions are not the same here like they were in the problem where we had it balanced in the middle. But it also adds a lot more work to our plate in the process. Now we could have gotten cosine of 45 and cosine of 30. Sine of 45 is all decimals. That's fine if you want to do it that way and not have all these cosines and sines in there. That's totally fine. Just be aware that you might end up rounding off and getting further away from these two answers, but that's okay. And that's actually what they did in the textbook as well. So if we go back and look at that, you can see here they do similar work. There's our two equations that we talked about. So they do go ahead and get decimals, and that's totally fine. Again, and they solve for T2 first, then plugging it in to solve for T1 as the actual answer first. You can see all the decimals they have in there. And they rounded too. So T1's 108, T2's 132, again, because they rounded. But even if we rounded the two answers we had to whole numbers, we'd get the same thing. And that's fine. So this talks about how normal force works. We haven't really talked too much about that, but how it's working against, and this one actually brings up the elevator ride, which we did do in class, and how it would act if you put it in an elevator and moved the elevator up and down. So that's what we're seeing here. So I'm going to just go quickly through this one real fast. I'm not going to actually do the work. I'll show you what they do. So here's our initial drawing of the person standing on it. They're looking to find two things actually with this problem. So A is the acceleration upward at a rate of 1.5. We want to find the scalar reading if it's accelerating upward or moving at a constant speed upward. So for A, it's pretty self-explanatory. There's a lot of forces you can see going on there, but really the scale is just going to read the combination of the person as well as the mass times acceleration of the elevator. When it is just the person standing there moving at a constant velocity, it's still reading his weight. So that's what's going to be going on here. So you can see here for part A, there's the combination of the mass times acceleration and the weight. So multiplying all that together, we just multiply his mass times both gravity and, well, they really messed up the exponent there on this twice. It's interesting for the acceleration. Anyway, so 75 times 1.2 for the acceleration that it's moving with, and then 75 times 9.8 for the weight portion of it. Combining that together gives you 825. But for part B, so this is actually calculating part A, getting his weight, and that's actually the answer for part B. So there you go. So here's those problem-solving strategies we saw before. Again, looking at it in terms of Newton's laws. All right, so for this problem here, we have a soccer player that's starting from rest, accelerates forward. So we have this velocity that he reaches and the amount of time it takes. So for part A, we're just looking for average acceleration. If you remember average acceleration, take a screenshot. Right on the screen as it was. Wasn't going to work. So average acceleration is just the change in velocity over change in time. Starting from rest, so that means our initial velocity is 0, final velocity is 8, so that's our change. And then the amount of time is the 2.5. So dividing that out, 8 divided by 2.5 is 3.2 meters per second squared. So we've got our acceleration now. For part B, we're looking for average force. Well, that means we're going to take this acceleration and use that with the mass that they're giving us, 70, to find our force. So pretty straightforward there. So the force is equal to ma, force, Newton's second law. So that's 70 times 3.2. Our force then is 224 newtons. And of course you can see their work here as well. Same process, got 3.2, and then multiply that by the 70 to get 224 as well. So now getting into the 4 basic forces. So this one's just talking about how there are 4 basic forces, and really the ones that we are more directly experiencing than anything is the electromagnetic force and gravitational force are the 2 that we mostly feel. But the most common one is the electromagnetic. So these are the 4 basic forces. Gravitational and electromagnetic, as we mentioned, and then the weak and the strong nuclear forces. And there's a table coming up here in a second that summarizes things about them. So the main thing here is that the ones that we are going to really deal with in this class is really just the gravitational force. Electromagnetic is more geared towards AP Physics 2. And then the nuclear ones do come up in AP Physics 2, just not in great detail because they require a lot of calculus to deal with them. And AP Physics 2 also is not calculus based. So given the options, which one of these is not one of the 4 basic forces? So gravitational, as mentioned, is the most common one we are going to deal with in this class. Celestial, not one of the ones we mentioned, so that's it. Nuclear has both the weak and strong, and electromagnetic, of course, is the one you'll see mostly in AP Physics 2. So here's that table of information about the 4 basic forces. You can see there's a lot to do with the gravitational, all of them, but just some interesting information about them. Not much that we're going to really see so much, but it is important to know that they exist, and that in relatively the gravitational force is the weakest of the 4 basic forces. If the strong nuclear has an approximate relative strength of 1, gravitational is 10 to the negative 38. That is tiny in comparison to the 1 that the strong nuclear is. Electromagnetic is the second strongest, and then weak nuclear is the 3rd from there. But do notice that the only way the attraction or repulsion works for gravitational is attraction only. It does not repel. The other three all can repel as well. So again, despite the fact that we feel it the most, it is the weakest of the forces, the gravitational force, that is. But it has a lot to do with very large-scale things. So that's why it's something we can feel more than the other ones.